This is lecture 18, and in lecture 18, we are going to continue talking about clustering. So let's do a real quick kind of recap of what we talked about last time. And the main focus last time was we talked about K-means clustering. And we had built this up in the context where if I have some x, and it's some n by p matrix of covariates. What do I want to say? If x that n by p, that's not the sentence. If x is a n by p matrix of numeric covariates, and for clustering we have to define a dissimilarity. And we had developed K-means in the classic context where I define my dissimilarity matrix that we're calling D, which tells me pairwise the dissimilarities between my I and jth observations. And I define this in this case so that the dissimilarities is literally just going to be the Euclidean distance between my points. And since my points, my xi's, are numeric, if I have two xi's, I have xi and xi prime, let's call it, I can just look at the Euclidean distance as all numeric data, and I can call that a dissimilarity. So distances are dissimilarities, but not all dissimilarities are distances. And we were trying to solve the kind of combinatorial clustering problem. So let's say the combinatorial clustering problem. Again, let's try spelling correctly. And combinatorial clustering meaning basically I'm just interested in putting things into groups. I'm interested in dividing things up into groups. I don't have a very strong probabilistic model I'm basing this on. You can view it in some ways, and it's a little more advanced than we'll talk about, but you can view it as some kind of probabilistic model. But our combinatorial problem is basically we want to choose some G's, that is, some groups or clusters, G1 to some G capital K, so that if I have my within cluster, kind of total within cluster dissimilarity, which I could define as, so it's, this W is a function of my group assignments. So I'm going to have some kind of putative group assignments, G1 to G capital K, and I can calculate my total kind of within cluster dissimilarity by, first, for a particular cluster, I'm going to sum over all pairs in that cluster, and I'm going to sum up the dissimilarities of all pairs in cluster K. So how I have to write this, I'm going to sum over I and I prime that are in group or cluster K, and I'm going to sum up the dissimilarities of these, I prime, and then I'm going to sum this up for all clusters. Now, sometimes people like to put a 1/2 out front, and that just doesn't actually change any of the math here. It's just a cute little thing to make some of the kind of theory behind this a little cleaner to do. One way of thinking about it is that I'm summing over I and I prime, so I'm kind of double counting. I sum over 1 and 2 and 2 and 1, right? So there's some reasons why people like to put that 1/2 there, but it's not particularly important. And so I have this kind of total within cluster, or within cluster dissimilarity, or within group dissimilarity, and I wanted to minimize this. So we choose our G's so that this thing is minimized. And the kind of combinatorial problem is, how do I divide up my data points into my groups, my G's? And so basically we're optimizing, I could say, i.e., if my final group assignments maybe are G1 hat G2 hat, you know, dot, 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 up to GK hat. This is going to be the G's that minimize this W of my G's. Okay, so that's a kind of really formal way of writing it. We can show, indeed, that this is equivalent to minimizing the following quantity. In fact, we can show that W, in fact, W is equivalent to the sum over my groups. And then I'm going to basically look at, weight them by how many observations are in my kth cluster. So this is number of observations in kth cluster as given by the G assignment. And I'm going to sum over all I in that cluster, and I'm going to sum the Euclidean distance of xi to the mean of that cluster. So it turns out that we can show that W is equivalent to this thing, and therefore it is equivalent to minimize, to find my groups so that I minimize this criterion, which is basically minimizing, choosing my G's so that I minimize the distance of any of my points to their, to the mean of the group. So because we have multiple x's, this x bar is not just a number, but this is actually a vector. So this is a p-dimensional vector. If I have p variables, this is going to be a p-dimensional vector of the kind of column-wise, or the column-wise or element-wise means of my x-bi's. So it'd be like if I summed up some of the rows of my kind of vector added rows together of my X matrix and then divided through by how many added up. That's where you're going to get. So we can actually show this, and it's worth talking about it for a hot second here. So our original W, of course, was the sum over II prime in GK, and then I look at, I look at what the dissimilarity of I and I prime. Now, of course, we know that for this case, this dissimilarity between I and I prime, we've defined this to be this Euclidean distance squared, all right? And so we can take a look at this Euclidean distance squared, and I can say that xi minus xi prime squared, norm of that, is the same thing as xi minus x bar for my group plus x bar for my group minus xi prime, right? So I can add and subtract my group mean. That doesn't change. That certainly doesn't change anything because that's just adding 0. And then, of course, I can write out norm of something squared, right? Say the norm of vector A squared is just A transpose A. So I could certainly write this out as xi minus x bar plus x bar minus xi transpose that whole thing again. I'll just leave it like that. Maybe we should bring this over here just to give us some more space. And then what I'm basically going to do is I'm going to group together the first term and the second two terms here. And when I square this out, what I'm going to get is xi minus x bar transpose xi minus x bar plus x bar minus xi prime transpose x bar minus xi prime. Right? This is basically like a FOIL method, right? We're just first squared, last squared, and then I'm going to have what? I'll have two of the cross product terms, which is going to be xi minus x bar transpose x bar minus xi prime. Okay, so that was this kind of part, this inner part here, right? So this is a really classic trick to do this kind of thing in statistics. And if I bring this whole thing down, remember we're summing over a bunch of things. So we're summing over k, 1 to k, and then we're summing over I and I prime, all pairs I prime in my group. And so if I take this thing and I plug it in here, of course, what am I going to get? So I can actually distribute the sum across. I have two sums here. So this is going to be, well, let's even simplify it further. This first term here is, of course, xi minus x bar squared, the norm of that thing squared. And the second term here is xi prime minus x bar squared. And this third term is what it is. But I'm going to get xi minus x bar squared plus xi prime minus x bar squared. And then I'm going to distribute my sum, just for the sake of readability. And I'm going to get, well, I get a 2. I can bring that 2 out. And I'm going to get this cross product term. So it's xi minus x bar transpose x bar minus xi prime. Okay. And my claim is that this last term here is 0. And the reason it's 0 is because I could distribute my sum through is basically, we know about means is that if I look at the sum of xi minus its mean, that's 0. And that's basically what's going on here. We have the sum of xi minus x bar. This is transpose, it's a vector, but it doesn't matter. You're going to get the 0 vector at the end of the day. And so you're going to get 0 for the last term. So it actually drops out. And so what are we left with here? We have our sum over k's on the outside. And then I could write this as the sum over I and the sum over I prime. And what am I summing? I'm summing this thing, right? It's a horrible expression. We're almost there. Okay. So we're summing that thing up. Now, the innermost sum depends on I prime, so it doesn't depend on xi. And so I could actually bring this thing out of that sum. It doesn't depend on xi. And what I'm left with is the sum of xi. I'm left with that sum of xi prime minus x bar. I'll be left with that in the inner part there. You know what? This is going to be easier to see if we do it this way. So let's just do one more little step. Still my sum of my k's on the outside. So let's just be lazy. It's the sum of the I prime, and then I'm summing up xi minus x bar k squared. So that's one thing, kind of in my bigger thing. And I'm just going to distribute both of these sums over, plus sum of, and I can actually interchange the order. I'm going to say sum of I prime I xi prime minus x bar k quantity squared. All right, so that's my second thing here. Okay, so again, if I sum, so for this, just consider this first one is I'm summing up this thing, which doesn't depend on I prime, so I'm just going to get n times, or I'm going to get nk times. So this is just nk times that, and I'm going to have a similar story here, because, you know, it's like if I sum up 1 n times, I'm going to get n times 1, right? So here n is the number of things in that cluster G. And so what I'll be left with here, we're almost there, is I'm going to get the sum over I, nk, of this thing. So this is all my big sum there. And then I'm going to do a similar thing. And here it should be the sum over I prime, but that's a dummy variable. So I could just say it's sum over I. It doesn't actually matter what the dummy variable is called. And so these are the same. So this is just 2. Well, let's write it. Yeah, let's write it this way: 2 nk sum Okay, and that's what we get. And of course, we have this 2 floating around, so you wonder why you might want to divide w by 2, is if I properly were to put a 1/2 out front here. So if I were to, oops, so that's correct. If I put this 1/2 out front, I'll carry around this 1/2, carry around this 1/2, and then at the very end, of course, that will cancel with my 2, and I'll get exactly what I claimed. And so an equivalent way, and a way you often hear this talked about, is it's the within cluster sum of squares, right? Because it's basically the sum of squares within each cluster, and then the total within cluster sum of squares. So often it's called total within cluster sum of squares. More generally, for any dissimilarity measures, it would be the total within cluster dissimilarity, for example. So what's the point of this horrible algebra, besides having some fun? We made the claim that we were minimizing this thing. And if we made the assumption that our data was numeric and that we use a particular dissimilarity, we could show that minimizing that, W, was equivalent to minimizing this quantity. And our proposed algorithm Lloyd's algorithm, and I won't write it out in full detail, but basically Lloyd's algorithm said that I iterate over some index, let's call it t, 1, 2, 3, etc. And on my first step, I update some mu for each of my groups, so mu k at time step t is just going to be 1 over the number of things in group k times, it's just basically the mean of the things in group k. So I look over I in group k and I sum up my xi. This is group k at time point t, right? Because we're going to updating these groups over time. Cool. So that was our update step. And then we assign was our second step. And the second step was we basically say that the kth group at time t is going to consist of all those xi where if I look at the distance of xi to mu k at time t, so this mu k just calculated, if I look at that distance as measured by our Euclidean distance is going to be less than or equal to the distance of xi to any other k prime, let's say, at time t, for all possible other groups, k prime. So that is a kind of fancy way of writing what my group assignment is. The simpler way to say it in words is I just assign my xi's to the group to the group with the mean that it is closest to, right? So that's all Lloyd's algorithm is. But what you can see the connection now is that when we've rewritten k-means in terms of minimizing this thing, which is basically the distance of all these points from the mean. Now, the general general k-means algorithm is just minimizing that total dissimilarity. In the case of Euclidean, you can look at it as minimizing the distance of each of the points in my clusters to their means. You want to choose your clusters so that if I look at the distance of the points in each cluster to the mean, that is the smallest possible. And Lloyd's algorithm basically goes, it updates the means, and that assigns things in such a way that it should minimize this metric. And then it updates the means, and then it minimizes that, and then it updates, and then it minimizes it. And so the question is basically, why does Lloyd's algorithm work? Why is this achieving what I want it to, right? I want it to minimize this quantity, which we've mathematically shown is basically are within cluster kind of total dissimilarity. And so one way you can think of this is we could generalize. So let me say the problem that we wanted to solve, obviously, is we wanted our estimated groups, or our clustered groups, G1 to GK, let's say. We wanted to choose those so that they were the groups that minimize W, which, what did we write this as? We said that this was the sum over K times NK times the sum over I in group K of xi minus the mean for that group squared, right? So that's the problem that we want to solve. That's what Lloyd's algorithm wants to solve. And Lloyd's, so how can we show that this solves Lloyd's? Is we can generalize the problem and we could consider the minimization problem not only over the groups, but over the means. Let's call them M1 to MK. So these M's are going to be basically our centers, or our means. And we want to minimize this now. We're going to kind of generalize it by saying the criterion we want to minimize is NK, sum over I in my group. And now instead of writing X bar, I'm just going to say it's some M, right? And so this is kind of a more general form of it. And if I look at it this way, Lloyd's algorithm is basically first minimizing over the M's, and then minimizing over the G's, and then minimizing over the M's, and then minimizing over the G's, and then given those G's, minimizing over the M's, and then given those M's, minimizing over the G's, and it's iterating back and forth and solving this problem piecewise. First G's, then the M's, then the G's, then the M's, then the G's. Why? Because if a kind of general fact is that X bar, if I have just any set of points and I want to minimize the squared Euclidean distance between my points and some number M, that is X bar. That's a way of defining X bar. It's the point that minimizes the squared distance between that point and the points in my data set, right? And so when I minimize over these M's, I'm basically solving that problem. So one way you can view Lloyd's algorithm is the first step. It says minimize, choose the M's to minimize this thing, right? So here's kind of my new objective, my more general objective with a general M. And basically I'm going to say minimize over M. Well, how do I minimize over M? You're going to choose X bar as M. And then I'm going to say, okay, given that, how am I going to choose my groups? Well, how should I choose my groups to minimize this thing? I should assign things to their closest mean. That would minimize that criterion. And so it iterates back and forth between it that way, right? So let me just write this out. So step one basically says, given my group assignments, set MK to be XK, and this reduces W. It will minimize this W, so this is what I'm calling W here, because if I hold the G's constant and I say, what M's should I choose to minimize W, I should choose M as X bar for the group. And so this reduces W. And then my step 2 says that if I hold my M's, I'm going to choose my G's as points closest to my M's. And that obviously is going to minimize this criterion. If I have this criterion, how should I choose the elements to be? If my M's are fixed, how should I choose my elements to be in my group to minimize this criterion? Well, I should choose the points to be in the group to be as close to the mean as possible. Because otherwise, if I choose something that's not as close as possible, or as close to its possible mean, I could make this thing smaller by assigning it to the group where it's closer to that mean. So this will also reduce W, which is the whole name of the game, right? We're just trying to minimize W, and so if I can reduce it at each step of my algorithm, I'm getting towards the minimum, and that's the whole game. So the punchline is that at each step, this makes W smaller, and so if I do this enough, we'll eventually converge to some kind of answer, right? And so the idea is that Lloyd's algorithm is just iterating back and forth between one way of viewing. I mean, practically this is not how you calculate it, but the way of viewing and why it works is that you're holding the G's constant, minimizing the M's. You hold the M constant, you minimize the G's, right? So you can minimize or maximize any function one coordinate at a time. You can minimize over X, then over Y, then over X, then over Y, then over X, and eventually you get to the right answer. You're totally allowed to do that. And that's all we're doing here in a kind of more complicated way. And so because at each step we know this has to decrease W, this procedure over time will decrease W and get us towards some kind of answer. Now, it doesn't mean we necessarily get to the global optimal solution. So the big caveat is that we don't necessarily get to globally optimum solution. So again, this is the realm really of Dr. Kincaid, who does discrete optimization, but I can do my best impression here, right? So if I have, this might be W. So this is, let's pretend that my x-axis is like G's, whatever that means. So really it's this multi-dimensional complicated space, but if you pretend it's a one-dimensional problem, and I have my red curve, which is maybe W of my G's, right? And this is maybe not the best red curve. Let's draw a slightly less insane red curve here. Something like this. Okay. So depending on my real first step in my Lloyd's algorithm was to initialize my groups randomly. So I initialize my groups randomly, and I land in a random place in this space. Now, there's a whole literature on how to do this well, because if I initialize my groups randomly and I land here, at each step, I'm guaranteed to take a step lower. And so if I initialize here, say t is 0, and I take my steps, I'm eventually going to get stuck in this local minimum, because Lloyd's algorithm will not take a step higher because it doesn't know that there's a better solution over here with a lower within cluster kind of dissimilarity. And it refuses to take a step that hurts it at all. And so it will get stuck here. And you'll get a solution with a locally optimum solution. Alternatively, of course, if I were to initialize my guess here and say this was t equals 0 for a different random initialization, and I take my steps down here, I'm going to step down my curve at each point. I am guaranteed to decrease W at each step, and eventually I'll get down to here, which is my best optimum, globally optimum solution. So while Lloyd's algorithm will get us to some optimum, it might be a local optimum. So this is our global optimum, and this is kind of not where we really want to be. This is our local optima. Okay. So the solution in practice, and there actually has been quite a bit of literature on this, is we're going to try several random initializations and take solution with the lowest W. And that's practically how you do it. You can do it a bunch of times. Depending on how complex your data is, that could be computation intensive or not. It could be easy. Okay. So that's kind of a little bit more of the theoretical background of what's going on with K-means. So here's the question. I don't want to spend too much time on this, but we should spend about, I don't know, a couple minutes talking about this. What about non-numeric data? And, you know, or even non-Euclidean distance or dissimilarity, right? So all of this is predicated on our calculations done with the Euclidean distance. What if we even just, you know, Euclidean distance, you know, weights things far away from, you know, in this squared way, and that kind of weights outliers very heavily. I mean, if we don't want to do that, when we use like absolute value or something, what do we do? Because all of our math was based on this this Euclidean distance, and this is an algorithm called kind of just an alteration of K-means, and it's called K-Meteoroids. And they're not necessarily means, but they're meteoroids. And the basic idea, the solution here, is that what if we don't have any numeric data? We just have D. Maybe we just have our dissimilarity matrix. We don't even have a notion of means. We don't even have a notion of data points. We just have a dissimilarity matrix for our objects. The solution here is basically to replace step 1. So step 1 was when we calculate our means, was update our means step with by using setting mk, as we had talked about before, to be the closest, the point in the cluster closest to everything else. Everything else in the cluster. Right? So if this is called K-Meteoroids, and we can do this purely in terms of dissimilarity. So so effectively we're actually going to use this generalized version of it, because now we're actually going to have to solve an optimization problem for the MKs. We just know a priori we can't use this fact that X bar solve this, because we don't have a notion of X bar. We just have dissimilarities, and we're just going to find the point that kind of minimizes, that solves exactly this problem. Okay, so step 1 star, let's say. Now our update step is we find observation and cluster closest to others. So it's a little notationally cumbersome. Let's call it I star, so the index star being the optimum index for cluster K, and that's going to be, we're basically solving the problem of we're looking over all the things in our cluster, in our Kth cluster, and we're going to look at the kind of total distance of some other I primes to I. So we look at overall I in our cluster, what's the distance, the total distance of I to everything else in the cluster, and we're going to choose for that cluster the I that's kind of most centrally located. And so we let M K be M, yeah, we let that be the kind of, well, we don't even have a notion of X. We don't need a notion of X. So that's the deal. And our second step, our assignment step, is basically the same thing, where we say object I goes in group GK if the distance of I to I star K is less than the, not distance, but dissimilarity of I to I star K is less dissimilar than I to I star K prime for any other K prime, right? So this looks a hell of a lot like our KMeans algorithm, but now it's all in terms of dissimilarities. We don't even ever talk about the x's. So the nice fact about this is that no x, we just need our D matrix. We never even talked about x's. The kind of bad fact about this is that it's more computationally intensive. Because we have to solve an explicit optimization problem. So this is an explicit. Before, with k-means, we were able to just calculate the means, and we didn't actually have to calculate, we didn't, when we were finding, theoretically, you could view it as optimizing and finding these m's here. We didn't actually do it. We just calculated x bar because we know x bar solves that optimization problem. The problem with k-meteoroids is that, while it's more general, we don't actually have to have x. We don't have to use Euclidean distance. We just have to have a dissimilarity matrix. It requires that we actually solve an explicit optimization problem to find the meteoroid at each step. So you do actually have to alternate. Find the meteoroids assigned to the group with the closest meteoroid. Calculate, find the meteoroid in new groups, assign in that way. But otherwise, it's basically the same thing. You iterate back and forth until your assignments kind of settle down, and you call that convergence. So the last thing I want to say about k-means is I want to talk about how do I choose the number of clusters k. And in general, there's no simple answer, right? If I look at a graph of w versus k, this is basically a monotonically decreasing graph, because as the number of clusters goes up, what we get is that the within cluster sum squared goes down basically monotonically. Why does that make sense? Because if I have more clusters, if you imagine I let, this is kind of like k and n, right? If I let k go to the number of points I have, I'm gonna have one cluster each with 1 point, and they're all gonna be perfectly have zero dissimilarity with their own point, zero distance from their own point, and so my total w is going to be 0. And if I have a few clusters, you're going to have things further away from that meteoroid, or more dissimilar with that meteoroid. So k more or less is going to kind of monotonically decrease, and so you can't just so like k and n. Can't choose k in this way, fortunately. One way is, however, to look at this graph and say you plot w against k, and you look for, let's call a knee or a kink here. So maybe it initially decreases really fast, and then it slows down. So this is either called a kink or a knee. And the idea is you might choose k star, the number of things, the number of groups you think your data has, by picking a point where there's a kind of abrupt change, where it stops decreasing really fast. The idea being is that if there truly were some underlying structure in your data of some k star number of clusters, then up until K star, you'd expect to get better and better and better clustering by a lot. But after you move beyond that, you're not actually capturing real structure, you're just capturing some noise. And so you would expect it to not capture as much. Super heuristic, not particularly mathematical. You could do a similar thing for choosing the number of principal components, choosing how much to reduce the dimension of your space. You can play a same game there with the variances against the number of components, and you look for a knee. And this is basically as sophisticated in 2021 as people are doing with it. And so it's very much an art, and this is why kind of unsupervised learning often makes people a bit uncomfortable, because there isn't a really well-defined answer about how many groups are there. Well, I don't know, because we don't have training data that tells us, no, that's right or that's wrong. Kind of an art for us to think about. Okay, so that's kind of a real tour de force of KMeans. And that's basically all I want to say about KMeans, K-Meteoroids. It's actually just a nice little algorithm that's kind of intuitive in some ways. And it's just the real classic clustering algorithm. In the last couple minutes here, maybe 10, 15 minutes we got here, I want to talk about hierarchical clustering. So I want to talk about another way of doing clustering. So hierarchical, hopefully that's how you spell that, clustering. Okay, so the thing about K-means is you have to choose this value of K. And one way to get around that is by, instead of building just one set of clusters, you build a hierarchy of clusters. And you kind of can look at this hierarchy to kind of figure out what the clustering might be in your data. And so basically what we're going to do with hierarchical clustering is we're going to build a collection, really a hierarchy, of nested clusters. And so how are we going to do this? There are a couple ways of doing this. One is called a agglomerative clustering. And the idea with agglomerative clustering is that I'm going to basically do it this way. I'm going to start with clusters as individual points. So I'm going to start with each point I have as its own cluster. And then I'm going to merge clusters that are, quote, similar or, quote, close. And thereby reducing the number of clusters I have. And then I'm basically just going to recursively repeat this until everything is in one cluster. So it seems like a weird description of an algorithm, but it's actually not so bad if we look at an example. So here's my example. I'm going to have points. I'm just going to label them 1, 2, 3, and then I have some other points over here, 4 and 5. And I'm going to build up a tree. I'm going to build up a hierarchy. And my hierarchy is going to start where each point is its own cluster. So here are my clusters. I have 1, 2, 3, 4, 5, or I should put a dot here, 5 clusters. So let's put those as my 5 points at the bottom of my hierarchy. And then I'm going to merge clusters that are close. So maybe, I don't know, clusters 1 and 2 are kind of close to each other, let's say. So I merge those. And okay, so I'm going to merge these into the cluster 1, 2. And then maybe cluster 4 and 5 are the next closest clusters. So I'll merge these into cluster 4, 5, like that. And then I'll say, okay, 3 is clearly close. The 3 cluster is closest to the 1, 2 close cluster. So I'll merge that into a cluster. So this will be the 1, 2, 3 cluster. Oops. How do I do this? 1, 2, 3 cluster like this. I'll merge that. And then we only have 2 clusters left, so the overall closest cluster, they all have to merge into one. I'll have my 1, 2, 3, 4, 5 cluster. Just merge them. So that's exactly what my algorithm said. I start everything as an individual cluster, I merge nearby clusters, and I keep doing this until everything's in one cluster. And that's called agglomerative clustering. Super simple. It's really nice. There's another way of doing this, which we're not really going to talk about, but the other way of doing this is called divisive clustering. Divisive clustering. Man, I wouldn't think writing so hard. Clustering. And divisive clustering is basically the opposite. And we basically start with one large cluster, and we're going to recursively break into smaller clusters. Divisive clustering has not been studied nearly as much as agglomerative clustering, and so we're really not going to talk about it too much. There are some techniques out there, but it's a much more complicated procedure for some non-intuitive reasons. And I could draw a little picture, but it's not even worth it. So let's talk about agglomerative clustering, because that's frankly when people talk about hierarchical clustering, that's what people mean. So we've talked about, if I have my points here, I talked about dissimilarities. Now I've drawn it in some two-dimensional space for visualization purposes, but it doesn't need to necessarily be in a two-dimensional space. And all we need is the dissimilarities. So we can measure dissimilarities between points. And we also, to do this kind of agglomerative cluster, we need to have some measure of closeness between clusters also. So let's write that down. To do agglomerative, you love the words people come up with. To do agglomerative clustering, we need a measure of, quote, closeness between clusters. So we have a measure of kind of closeness. You could also say similarity between clusters. We have a measure of similarity or closeness between points, between objects, but we need some kind of measurement of similarity or closeness between clusters now. And because if we can do that, then we can define what's closest, and then we just merge the closest ones, and we just do that recursively, and it's pretty simple. And there are a couple ways of doing this. So the three most popular measures of closeness are, say, single linkage. And single linkage basically means that the closeness or the distance between clusters G and H is the minimum dissimilarity, or you can think of it as distance, between any 2 points in G. Any 2 points, let's say one of them in G and one in H. Again, it's kind of cumbersome to write out in words, but it's not too bad. So again, we can visualize this kind of as distances. So here are my 2 clusters, maybe, and these are my points here. So this is my cluster G and this is my cluster H. And single linkage just says, I'm gonna look at all pairwise distances, and I'm gonna say the closest distance is the distance between my clusters, the similarity between my clusters. So maybe in this case, maybe we'll make it obvious. It's something like this, and there's a point here like this. So this is going to be my single linkage distance. This is distance SL, single linkage. And you can, of course, write it out mathematically. Single linkage between G and H is basically the minimum where I is in G and I prime is in H of dii prime. So again, we're able to totally describe this algorithm in terms of just a dissimilarity matrix. We don't even need x's. We just need some metric of dissimilarity between objects, which makes it super general. The other kind of popular ways of doing this are, let's say, what's the other one? Complete linkage. So the opposite of minimum would be maximum. And that is basically called the complete linkage. And I'll just really quickly summarize this by saying that it's the max distance, or let's say dissimilarity, between 2 points across clusters. So again, if I have my picture to keep in mind here is I have my 2 clusters, something like this, and I kind of look at all the pairwise distances, and maybe this point is far away from this point, and so this distance here is called the complete linkage distance, or dissimilarity. And of course, you could write down mathematically the complete linkage between 2 clusters G and H, so these were my clusters again, G and H, is going to be maximum, where I is in G and I prime is in H, of the dissimilarity of I to I prime. So it's basically the maximum distance between any 2 points, where one is in one cluster and the other is in the other cluster. And the third most popular way is called average linkage. And you might imagine that this is just the average dissimilarity between clusters. And I'm just going to write the formula because the picture is not really going to do us much good here. So average between G and H is I look at how many are in G, let's call that NG, and I look at how many are in H, let's call that NH, and I'm just going to sum over all I in G, and I'm going to sum over I prime in H, and I'll look at the dissimilarities. I'm literally just averaging the dissimilarity between the 2 clusters. So in a, if you have actually a kind of numeric data in some Euclidean space, then this is basically going to be the distance between their centers, is one way of thinking about that. And it kind of gives you, it's somewhere in between. So single linkages says 2 clusters are close together if at any point they're close together. Complete linkage says they're close together if all of their points are close together. And average says the typical one is close together. And that's, so that's the game. Basically, it's just an optimization problem. Again, it's kind of a combinatorial optimization problem where you look at all possible clusters and you calculate the distances and then you merge the ones that are closest together. The only last kind of really useful topic I'll mention here about hierarchical clustering is called a dendrogram. And this is probably why hierarchical clustering is so useful and people like it. Because this visualization called a dendrogram is super cool and super useful. Maybe it's not that cool. I won't oversell it. Okay, so let's look at a problem here. Let's say I have some points A, B, C, D, and then E and F. Okay. And I want to cluster these using whatever single linkage, average linkage, complete linkage I'm using, my collaborative hierarchical clustering. But I'm going to keep track of my distances. So I'm going to make a little visualization where my y-axis is going to be my distance, and I'm going to keep track of that over the course of my hierarchy. So the first thing in my hierarchy is to put all my points in their own clusters, right? And so the distances basically start at 0. So I have A, B, C, D, and then I have E and F. Okay. And so then I say, okay, what's the closest clusters? I'm going to merge those. And so maybe I say A and B by whatever measure is closest. And so I'm going to draw my hierarchy as before, but I'm going to make the height of how much I go up when I draw. I'm going to make that this height here is the distance between clusters. So the y-axis is the distance between the clusters. So I'm going to go up like this because the distance between these clusters is the smallest. And then the next closest cluster, let's say, is C and D. So I'll merge those. Now that has to be a larger distance. So my line here, if I project this over onto this axis here, it's going to be higher. So I'm going to draw it like that because it's has to be a larger distance. If it were smaller, I would have merged those first. And then maybe my next closest, these E and F are close, but a little farther apart. And so I'm going to draw that, and maybe it comes up to here like that. Okay. And then I merge again, and I say, okay, maybe, by whatever distance metric that the AB and the CD cluster are close, and they have some distance, either single, complete, or whatever. And I'll draw that on my chart. So the height of that thing over on my y-axis is basically the distance between these two clusters. The reason people use these three metrics is because the distance between my clusters kind of monotonically is going to increase when I use these things. And so my height here is going to correspond to the distance between these two clusters. And then my final thing I do is I merge all of them together. Okay, and that will have some height, and the height over here corresponds to the distance between that green cluster or my ABCD cluster or my EF cluster. And so I get this thing, and this is called a dendrogram. And the dendrogram, you can basically read off and look at the structure of your hierarchy. So AB is nested with A and CD are nested within ABCD, is nested within, and EF is nested within the whole thing, right? And furthermore, if I were to pick a point here, a cut point, and I were to cut this thing, and you can imagine cutting through the bars there, what would fall off would correspond to a certain clustering. It would be, if I cut at that height, it would be AB is a cluster, CD is a cluster, and EF is a cluster. If I were to cut at some higher height here, I would get the ABCD cluster are still connected and the EF cluster. So you can kind of cut. It would basically be like if I stopped my algorithm after the distance between these things hit a certain point, what would I get? What clustering would I get? When the distances between my clusters become too large, what would I get? And that is, you can kind of visualize it by cutting this dendrogram at a certain point. But it also just kind of tells you some nice, kind of the nice structure according to your distance metric. So it depends on the distance metric, but according to that metric, what the kind of clustering structure is in your data. So that is a real quick overview of hierarchical clustering, which is kind of nice sometimes too, but and it has this nice visualization, which is the dendrogram. But we're at time, so we'll stop there for today.